Guys, I'm really trying. It's too many things. But hopefully there's the notes. You guys, okay? Go back. And I have put in the time to put the notes together. They are distilled. They are basically every one slide has some meaning, has some message. Okay. Okay. So again, today the first hour we talk about the standard flame, not really artificial, but it's the simplest kind of flame, which is adiabatic, right, without losing anything, and which is not suffered by any aerodynamic effects. I'm going to define for you what I mean by aerodynamic effects, okay? But conceptually, it's a normal flame, planar. The flow is quiescent flow. All right? That's what it is. Then the second part, then I talk about what happens if there's heat loss. But even for this heat loss, I'm not putting any aerodynamic effects. I'm still arguing on the fact that you just have a planar flame. There's some kind of loss, okay? Radiative loss, but it's still kind of planar. Things are simple. But then through that, we were able to see, okay? Because the flame is becoming non-adiabatic. So you can see situations in which it goes out, okay? And particularly those turning points, S-curves, those turning points, okay? Catastrophic. The fact that you get those turning points is inherently the nature of nonlinearity in the problem. Nonlinearity because there's this exponential in the reaction rate. Okay? When everything is linear, you don't get this kind of things in static science because you put A, it gives you B, B is 2A, 3A, 4A, nothing interesting. All right? When things are nonlinear, you can get this kind of thing. All right? So that's what it is. Another thing, of course, with the standard flame, we talk about the chemistry effect, which has spent quite a bit of time. So this one, basically, will put a closure of premix flame. All right? So hopefully, after this one, you guys become expert in basic flame phenomena. Because yesterday, we talked about diffusion flames. Today, we talk about everything about premix flames. Okay? You should know. And tomorrow, we're going to do the final thing, and all the complex flows we'll cover it. I better have good sleep tonight. You guys better have good sleep. But again, I appreciate your guys' patience. I know it a lot of times it's too much. Well, what can I say? So okay, aerodynamics of laminar flames. So let's look at this. Okay. Again, we come back. This standard flame, okay, which I don't need to do it anymore. Then let's talk about some real flames. Real flames, one way I can say, okay, real flames, the flow is non-uniform, okay, and the flame is curved, okay, and it can be moving, okay. I cannot show it's moving, but it can be moving. Now, then there are two limits, two ways you can, two situations you can do. One, the same way we have looked at this, okay? Here we say the flame sheet limit for the fluid mechanics guys. All right? So again, for the fluid mechanics guys, I can have what's called basically a flame sheet limit, but we call it the hydrodynamic limit. Okay? The whole flame is a sheet, gets wrinkled. All right? You can do it for your turbulent flame simulation, whole flame. All right? I don't look into the flame structure. So everything is fluid mechanics. Navier-Stokes equation. No reaction. Now, the flame sheet itself can be a source of heat and mass, okay? It can be a source. Things can jump. But nevertheless, it's a flame sheet. And the other limit is, as what we have done, it's a reaction sheet limit, like this one, reaction sheet, okay? To do that. So therefore, we get this transport zone taken out, like here, this region. I got it out. Flow is still non-uniform here. Now, then finally, this sheet actually is not that crucial now. at this stage, okay? Reaction sheet. So frequently you can still treat it as here. But the reason is that it's so thin, the fluid mechanics effect actually becomes small. When the thing is really thin, fluid mechanics is basically convective transport. So it doesn't really change much across a very thin region. All right? Diffusion is important always. So okay, so that's what I want to discuss with you today. All right? Not today, this hour with things. And then I'm gonna emphasize to you different things. Okay, let's see what to do. So so fundamentally, with the standard 1D flame, the flame speed goes into several parameters. It's this the heat release, Lewis number, and the reaction rate. Okay, temperature is just adiabatic flame temperature depends on the heat release rate. A general stretch flame, as I said, again it depends on this parameter, flame speed. In addition, depends on two more. One is the loss parameter, which I just covered last hour, loss parameter. Another one is what's called the Karlovitz number. I'm going to define for you. Okay, Karlovitz number would represent the aerodynamic effects of flow non-uniformity, flame curvature, flame flow unsteadiness, everything under the sun, grouped into a single parameter. Describe it. Okay, that's the beauty of it. All right. So I'm going to say that. So when you have everything here, you can describe laminar flame in very general sense, with laws, with aerodynamics. All right? So the state of this understanding is fairly well. Now, I do have to say that not detailed chemistry, all right? Still within the realm of sort of one-step reaction. There are some detailed chemistry. There's some study there, but not too much. Okay. Another, just general concepts. System can become locally or globally non-conservative. I want you guys to remember that, okay? So when the locally non-conservative, you can get local extinctions, you can get flame holes, okay? Or your Bunsen flame, this way, the tip can open, okay? Due to curvature, local extinction. The Bunsen flame is not this way, huh? Local content. And that's local non-conservation of energy. And another thing you always want to remember, order epsilon modification of the flame temperature will lead to order 1 change in the flame speed. Is this clear? Because it's exponential, okay? When you change the temperature by order epsilon, you change the burning rate by order 1. So you draw your extinction because the flame speed changes by order 1, it dies, okay? You only need order epsilon change in the flame temperature. You don't need and you don't have order 1 change in temperature because the flame already died. You only need order epsilon. But frequently, it's very hard to see where you get the order epsilon, the flame speed, okay? So those are the things you want to recognize. All right, so I just want to briefly mention that, if you have a general flame surface, which is moving, and which is also situated in a non-uniform flow, all right? And then you can define, just really terminology I want you to know, a general sort of a stretch rate, all right? At least you should know. Stretch rate, kappa, which is the Lagrangian time derivative of the logarithm of the surface area of the surface, which is general, all right? 1/8 dA dt, all right? So this guy, the surface area will change because you have a flow. Your flow here, and itself somehow has some characters that will move, things like that. So area will change. So you describe the change of this area by 1/8 dA dt, and then you can do a basically calculus derivation of this unit surface vector. Then you end up with this general expression. I'm not going to go into it. I don't have time. But what this means that a flame can be subjected to stretch, okay? That means the surface area changes, stretch. By flow non-uniformity, obviously. By flame curvature, can also change its surface, okay? By its movement, can change its surface, obvious, okay? but also that the flame also, flame has to be oblique to the flow. You have the flame here, the flow has to be oblique to the flame in order to stretch it. Because if the flow is normal to the flow is normal to the flame, then it cannot stretch its surface area, right? It's normal. But if there's a tangential motion, it's going to move it. Okay? So those are the things. And also the flame has to be unsteady, VF, with curvature. So I do encourage you to sort of study a little bit of this particular. It's a very rich formula, right, with this thing. But this just, people in fluid mechanics know this. So let me just give you some examples of stretch flames. One is the stagnation flow, the counterflow which we studied, right? Okay, I told you there's a strain rate going here. So stagnation flow, basically, the stretch rate is basically K. A is basically the velocity non-uniformity, V equal to AY kind of thing. Expanding spherical flame, the stretch rate is basically dr dt. R is the flame surface area, 2 of R. So you measure the rate of change of the flame surface. You ignite a flame, it propagates out. It's under stretch because the flame surface area keeps on changing. Okay? And here, Bunsen flame, this way. If you look at the flow, it goes this way, and the flame is going this way, right? The flow is this way, so the surface area keeps on getting smaller. See that, right? If you follow the flow. So it's given by this expression. Now, notice, which I'm going to, the stretch rate in this one is positive. Flow this way, going this way. It's increasing the surface area. Outwardly propagating flame, positive. The flame keeps on changing with time. Bunsen flame, negative. Okay? As it goes, the surface area getting smaller and smaller. All right? All right? That's important because they behave totally opposite. Because one is positive stretch, the other is negative stretch. All right? Keep that in mind. Now, everything has an opposite. You have the real world, this is a forward stagnation point, you have a real world stagnation point. Go this way, okay? You have a sphere, the flow goes here, at the back, it's this way, okay? The other stagnation. You have inwardly expanding, inwardly propagating flame, okay? Right? Somehow you ignite it here, going this way. It can go. All my life, I tried to manufacture an inwardly flame. I still can't. I have this standard offer to my student generations. Very nice dinner, 3 dinners, if they can do this. You guys think about it. An inwardly collapsing spherical flame. Okay? Try to think of it. But anyway, this one. And then there's inverted flame. Because this curvature is different from this curvature, right? So, okay, so these are the kind of, so they are real flames. They are real flames, except we can't get this guy. But you guys know that in turbulent flames, you do have unburned mixture here, and the flame will collapsing to consume the mixture, right? Okay? So, all right. So that's one thing. Effect of stretch. The effect of stretch is that the hydrodynamic stretch, basically, if you think of it, it's let's go back, okay? Hydrodynamic stretch, you want to think of 2. The tangential motion of the flow basically increases or decreases my flame surface area, the tangential motion, right? Make it bigger or make it smaller. The normal component of the flow balances my normal component of the flame speed, the flame going this way. Okay, so what this hydrodynamic stretch does is it'll contort my flame topology, right? You do this, the flame would adjust to your flow, go here, go there. You see, the flame is a live animal. That's something I always tend to appreciate, especially premix flame. It's a live animal. You want to kill it, it doesn't want to be killed. It'll move to somewhere else and then remain alive. It will be killed until it absolutely cannot do anything. Then they say, okay, I give up. Okay? No, remember that. That's how I appreciate the flame. Yes, they do. Once it starts burning, it'll try to burn. It'll try to find mixtures here and there. Okay, so that's hydrodynamic. The reaction sheet limit is that in addition to this, you can see that through this diffusion layer, it enters in the reaction zone, and because of the different flow directions or something, the amount of species and heat could be all messed up. Okay? When you want to look at the structure. All right. Effect of stretch, right? Reaction sheet limit. So hydrodynamic. Okay, so let me just show you an interesting problem here, and which is a real problem. It's examples, okay? Corner formation, Landau propagation. If we have, this is a hydrodynamic stretch. I'm not looking into the frame structure. And also, what's called the Landau propagation is that the Landau is the first one. He says the flame always propagate with the laminar flame speed, which is the one we derived, which is not correct, actually, because due to curvature, due to something, they can change. But he said, let's assume it's always the laminar flame speed, okay? That makes the problem easier. So if you have a flame which is curved, let's just say, what is it, cosine x, okay? And then you let it propagate. The flame always go normal to each other. Not normal. Always go normal to the flame surface, okay? Right? So in this case, then you can easily see, in this case of this convex is concave, then the flame will always go towards each other, right? So whereas in this case, the flame will move away from each other. So therefore, in this case, eventually it will form a corner. Whereas in this case, it will stretch out. Okay? So by nature, just by the ability of the flame having a flame speed, this is the tendency they will always go, which is generally true. Okay? When you have whatever flame here, you shake it, whatever, it's gonna assume something like this. It will not go this. Okay? It'll go like this, with a fairly sharp corner here and with a smooth corner here. So that's general flame shape. So very, and then you can actually derive your relations, the state of corner formation, it forms. It's the same relation as you do. I don't know whether you guys have solved the shock wave formation, fluid mechanics. Same equation, Berger's equation. Very nice problem. So that's what this is. All right? So right away, without doing anything, you can do this. And this kind of things happen again in the physical sciences, just wave propagation, the behavior of waves. All right. So let me give you some physical concepts of what stretch does can do to your flame. All right. Let's look into the stagnation surface. This is important. Stagnation surface. The flow is this way, okay, divergent. And this is the reaction zone, and this is the diffusion zone, okay? Control volume. All right. Now, the flow is this way. Heat diffusion is going forward. Diffusion is always normal to my surface, right? So heat diffusion going this way, and mass diffusion is going this way, right? Okay? That's right. Now, the thing I want to recognize is that the heat diffusion is leaving my control volume going outside, whereas mass diffusion is entering my control volume inside due to this flow. All right? So what does this mean? If Lewis number is 1, we come back to our friend Lewis number. If Lewis number is 1, then they are of equal rate. Energy conservation. Okay. However, if they are not of equal rate, for example, if Lewis number is bigger than 1, for example, okay? if thermal diffusion is faster than mass diffusion. Right? Lewis number. So now we really come back to Lewis number. So if thermal diffusion is bigger than mass diffusion, Lewis number bigger than 1, then this control volume is losing energy if I stretch it. Okay? Does it make sense? It's losing energy. So the system is non-conservative relative to this state. So this mixture, as it goes to this case, when it's divergent, it's encountering this flame, and then it's losing its energy. Okay? Total energy. Is this clear? Right? Because again, thermal and mass gets out of balance. So therefore, if it's for Lewis number bigger than 1 mixture, under this situation, the flame temperature would decrease from its adiabatic flame temperature, would be reduced. Right? And then if you stretch more, you increase the velocity more, at a certain point, as I say, give up. Okay? It's losing so much energy, extinguishes. That's how you extinguish a flame in this situation. Right? So this is, okay, did I explain it clearly? This. All right. The interesting thing is that in this case, the reactants is all reacted, actually, out of here. So even complete reaction is still extinguished, right? Because of this loss of imbalance. Okay. So the next question to ask, you might want to ask, well, what happens if Lewis number is less than 1? Lewis number less than 1, that means it's losing so much energy, gaining species in terms of chemical energy, and if it's less than 1, this is more efficient. Okay? So for that case, Lewis number less than 1 now, okay? Lewis number less than 1 now. This mixture, when you stretch it, becomes super adiabatic. It's gaining energy. What does it do? Burns faster, burns stronger. So your flame temperature can go above your adiabatic flame temperature. Okay? In terms of NOx formation, it's going to give you more. Things like that. So then you say, how do I extinguish that flame? Because the stronger you stretch it, the happier it gets. Right? It says, hit me, hit me. You hit him, he gets stronger. Okay? This flame, that happens, that's real, okay? So what happens with this flame, it took a while for people to realize that, is that, let me still go back to here, is that eventually, as you stretch it, it's going to move, right? It's going to go back. Eventually, it goes to the stagnation surface. Then you stretch it, it got nowhere to go. Okay? It got nowhere to go, then reaction will be incomplete. You don't have enough time to complete. Then eventually it extinguishes. But that's another mechanism for extinction. That's incomplete reaction. All right? So now I hope you appreciate that there is a relation between stretch and the Lewis number. Right? I've been impressing upon you guys the Lewis number. Now it's a real big time Lewis number. Before, the Lewis number is not that big effect. This is a real effect of Lewis number because it changes your flame temperature. With the laminar flame 1D case, it doesn't change my flame temperature. It doesn't change much. But once you get the stretch in it, it changes the flame temperature big time. Big time like order epsilon. All I need is order epsilon. I can kill my flame. Okay? All right? So that's what this is. So that's with this one. So I hope you guys know, you can read this. Now, let me give you the other example, a Bunsen flame. Okay? Bunsen flame, what happens? If you look at this guy here, you see that gets here, and then there's a curvature here. Okay? Now, the heat and mass would go normal to the flame curvature. All right? Now, then heat diffusion will focus here, right? Heat diffusion. Sure. Because heat diffusion is away from the flame, away from the flame. Heat diffusion this way. Mass diffusion go this way. Okay? Mass diffusion defocusing. Heat diffusion is focusing. Okay, tell me then what? I have Lewis number which is bigger than 1. Lewis number bigger than 1. Lewis number bigger than 1, thermal diffusion is stronger than mass diffusion. I'll make the flame what? Go stronger. Okay? Right? Thermal diffusion is stronger. More focusing of heat than defocusing of mass. So this curvature will make it burn stronger. For Lewis number bigger than 1. Again, Lewis number bigger than 1. Go back to the previous figure. Lewis number bigger than 1 goes weaker. Remember that? Previous one, Lewis bigger than 1 is weaker. This one, Lewis number bigger than 1 is stronger. Why? Because the stretch. This is a negative stretch, I told you guys. The surface area decreases. Stagnation flow is positive stretch. Okay? All right? So it might take you a little while to sink in. All right? But once you sink in, you can play magic. All right? You play around this way. Plus, minus, plus, minus. So Lewis number, bigger than less than 1. Stretch, bigger than less than 0. All right? I'll show you they come up together as a single parameter. So the single parameter when it's bigger than 1, less than 1. Bigger than 0, less than 0. Okay? So this, I guess, it's real, okay? You got situations when Lewis number bigger than 1 is super adiabatic at the tip. You look at the flame, Bunsen flame, for that case, the tip burns stronger. Brilliant, bright. All right? Whereas you work this kind of case, your tip extinguishes, opens, that's what's called. So then when you open tip, you got soot coming out. But anyways, open tip. All right? So you translate it to your turbulent flames, and you people study turbulent flames. It's obvious. Your flame got curvatures, wrinkled here and there. So you could put situation you get holes, or you get bright spots occurring. Local extinctions, your vortices, which is stretch. Okay, your vortices, which is stretch here and there. Okay. This I don't want to go. This similar thing, if it's expanding flame and things. So, again, I'm not going to go with this. This, again, it's actually a rather simple phenomenological analysis of a stretch of this counterflow flame, stagnation flame. All right. Again, I'm trying to determine the flame temperature, and then I try to get this burning rate out. Right? What is significant is that, again, I have sort of the flame speed. Let me see, what should I do? Eventually, the results end up with this S, which is the Karlovitz number and the Lewis number minus 1. Okay, as I said, Lewis number bigger than less than 1. So the relevant parameter is minus 1. So it's a plus or minus. All right. Karlovitz number is basically my stretch rate time, characteristic stretch rate time, to my laminar flame time. This is the laminar flame time. So that's my Karlovitz. So Karlovitz number represents my stretch. Lewis number represents my diffusivities. So you get this particular parameter as 0. But they come together. That's important. Okay? They don't come separately. They come together, which is beauty of the theory. Right? You have two different non-equal diffusivities and the fluid mechanics. They couple together. So you can have situation, this plus or minus 0, bigger, so smaller than 0, and this is bigger or smaller than 1. So you can have combinations. You can have, right? you can go, so this can go plus or minus. All right. So in the end, again, I'm jumping. Again, I was able to derive the flame speed for a general stretch flame, for that particular counterflow, but it's the same thing. I end up again, this formula. Remember the formula I gave you last hour? F squared minus F squared log F squared equals to L, minus L, okay? Right? And you promise you're going to recite it in your dream tonight. So during dinner time. Okay. So this guy comes back again. You know, the beauty of analysis comes back again. F squared log F squared. Because everything is involved the change of the flame temperature. All these things goes in change of the flame temperature. The change of flame, and then it goes into the burning rate. So it's the same thing, all right? So for that, the other one I have minus L, right? So this one I just call it sigma naught. So this minus sigma naught basically have the same rho as L. This minus sigma naught, it's beautiful parameter. It's this guy, okay? Karlovitz number, Lewis number, Zeldovich number. Because once I analyze the flame structure, I have the Zeldovich number come out. I want to really impress upon you guys this particular number. Now, there's no name to this, okay? We identified it. This is a powerful number. If you think deeper, a single number, a single parameter represents fluid mechanics, Karlovitz number, okay? This fluid mechanics itself represents the flow, represents the curvature, represents flame unsteadiness, all the good stuff with fluid mechanics. It's already a single parameter, fluid mechanics. Lewis number represents the transport property of the flow, okay? Zeldovich number we know, activation energy, heat release. Everything in my combustion system is there, indicated by this sigma. All right? So the whole flame response just depends on this guy. All right? So please appreciate, let me say, the beauty of this thing. All right? I mean, I look at it, I just feel amazed with this. Now, another number, just for your general information, it's called the Mach-Singh number. Mach-Singh number, basically, you just take this guy and this guy, okay? Zeldovich number times Lewis number. Why you want to separate out, put a Mach-Singh number there? Because this is system-dependent property. Karlovitz number, the fluid mechanics, depends on your flow. But this guy really just depends on your mixture. Okay? You give a Ling methane air mixture. You can calculate the Zeldovich number. Okay? You can calculate the Lewis number. You can tabulate. So that's why it's kind of useful number. You can, again, as I said, you can tabulate this for a given mixture, for anything. Mm-hmm. And then you throw in the Karlovitz number for the flow. Okay? Mm-hmm. So, yeah, so I'm just repeating this. You can see that it's sigma naught, it's reactivity, non-equal diffusivity, stretch, everything here. And then the beautiful thing, the kind of cute thing with this is that you can verify the theory, okay? You can verify the theory because this guy, as I said, okay, this guy, this S0, depends on, because the flame behavior depends on, whether this is plus or minus, right? And whether this is plus or minus, plus or minus, then depends on whether Karlovitz number is plus or minus, which itself depends on the curvature, depends on the flow, and also depends on whether Lewis number is bigger or less than 1. So you have all sorts of combinations. So it's fun. Then you go to the lab, you do this experiment, you change your stretch rate, you change your positive, negative, you change your mixture, make it Lewis number this way, that way. You can see the flame. Oh, all you need to say, oh, it burns stronger, it burns weaker. That's good enough. With this. All right. So, okay. So let me show you some results. one thing interesting, actually it took a while for people to appreciate it. Right now it's still not totally appreciated, is what happens for a flame in which Lewis number is 1. Okay, Lewis number is equal to 1. Lewis number equal to 1 for the longest time, people didn't appreciate the influence of Lewis number. Even now, then the general concept is that if you stretch a flame, the flame will get thinner. Okay, you stretch a flame, it will get thinner. But what they don't realize is that you stretch a flame, the flame will move away. The flame is not going to let you kill it. They'll move away. It will retain its burning rate, same thickness. Flame won't go. So what I'm saying here is that this guy says that the stretch is stretch and Lewis number, right? So the flame behavior depends on S. So if my Lewis number is 1, my S is 0, so the flame is not subjected to this stretch effect for Lewis number equal to 1. Lewis number equal to 1 flame is neutral, okay, to stretch. It's oblivious to stretch. Lewis number equal to 1. So remember that. It's a very good mixture to do experiments. You do that, then you can interpret your results much easier a lot of times. All right? Pick Lewis number, and usually stoichiometric frames are close to 1. All right, so to demonstrate this is that we have, what I have here is the temperature profile across a stagnation flame, all right, with different stretch rates. And then I measure the temperature. So different stretch rates, you see the flame temperature changes, okay? However, if I sit on the flame, then they collapse into the same part. Because if you stretch it, the flame moves. You stretch it, it moves. But if you just sit on the flame, collapse it, then it's the same flame. Okay? This is this Lewis number equal to 1 flame. So it shows that the flame structure really doesn't change when you try to stretch it, if it's Lewis number equal to 1. Adiabatic, okay? Remember, Lewis number equal to 1 is adiabatic system. However, if you want to, you go to non-equidiffusive mixture, it's called, for Lewis number which is not 1, deviating from 1, then it's rather interesting. Here are some typical things, and you can try, okay? For Ling hydrogen air flames, it's less than 1. Ling methane air flame less than 1. But rich propane air flame is less than 1. So Ling hydrogen air less than 1. Rich hydrogen is bigger than 1. And the rich methane air is bigger than 1. But Ling propane air is less than 1. Rich propane air is less than 1. Ling propane air is bigger than 1. Why this is fun is because, for example, if you change from Ling hydrogen air to rich hydrogen air, it behaves differently. Okay? Right? Because the Lewis number changes. What am I saying? I say Ling methane air? That doesn't matter. Ling methane air less than 1, rich methane air bigger than 1. Because for Ling methane air, the controlling species is methane. Rich methane air, the controlling species is O2, -1, less than 1, bigger than 1. So what is so significant? Well, if you are not aware of this stretch effect, okay? You're not aware. Never had any course in this. Especially if, for example, let me just, you're a chemist, you just everything, you interpret everything under the sun through chemical reactions, which is very complicated. You know, my full respect for them. But you don't realize this transport effect, okay? So you do an experiment. You do a stagnation flow, counterflow. And then you use Ling case. And you use rich case. You're doing. You are seeing things behave quite differently. So you scratch your head. This is Ling chemistry. Scratch your head again. That's rich chemistry. Okay? It's due to that. And you try to think of different reactions, try to do that. And you can always find some reactions when you do this. But then it's actually due to the stretch effect. Okay? All right. So, and similarly with hydrogen. Hydrogen is so strong because its diffusivity is so so fast. Hydrogen will really show you the effects. Okay? So you really have to understand this. So again, it's lean, it's going to cause it to extinguish. It's rich, going to make it burn stronger. Lean, well, depends on the Lewis number. So you guys look into this. These are the results. Some calculated, mostly calculated results. But you can see, counterflow flames. I've switched it lean and rich, for propane air and methane air, whatever. You guys can convince yourself. The flame speed would change. Okay? One is increasing stretch rate, increases with stretch rate, decreases with stretch rate, and all the good combinations. All right? So you guys convince yourself. Here are some experimental results. This is a counterflow. This is a counterflow that that's the state counterflow. You have a symmetrical mixture here. So you get two flames, okay? A premix flame, two flames, counterflows in this way. Now this is the state almost at the extinction. If you see, for example, lean propane air as its Lewis number bigger than 1, so when you stretch it, the flame temperature decreases, the flame would extinguish. Okay? You can see the state of extinction, the flame is separated. They will extinguish. However, if you look at the rich propane air, as you stretch it, the flame temperature gets stronger and stronger. Okay? So it will not extinguish until it goes to the stagnation surface. Then it has nowhere to go. Then you get incomplete reaction. Then it dies. Okay? So for this case, rich case, it dies when they are basically merged. And by the same token, my lean propane air should go with rich methane air. I think this one shows they are separated, if you guys look at it. And my lean methane air should go with rich propane air. See, this is again something you have to realize. If you don't, you try to explain it totally, again, as a chemist, you scratch your head. You see, is there a difference between lean chemistry, between my methane chemistry and my propane chemistry? Okay? Because when I change, my lean methane air behaves like rich propane air. My rich methane air behaves like lean propane air. All right? Then you say, what's going on? Okay? And similarly, you look at the Bunsen flame. You can see with this kind of lean propane air, the tip burns stronger. Okay? And whereas lean propane air here, it gets weaker, it extinguishes. And the rich propane air, the tip opens. I mean, those experiments are easy to do. You guys go back to the lab and set up a Bunsen flame and see it. Okay? You're going to see it. And that's what, a long time ago, we did it, just for fun. All right? Okay? Okay, I don't want to go into this ample demonstration that this diffusional, this stretch effect and the diffusional non-equal diffusion effect would affect the flame behavior. Okay? Okay, let me talk about flame front instability. So I'm done with that thing. I'm talking about flame front can go unstable. There are two modes of flame front instability. One is, let me just show you what flame. A flame, this is spark ignited flame. Spark ignited flame, okay? The flame propagating out. That's a slurring picture. Certain times the propagation is very smooth. Certain times the propagation is very wrinkled, pebbled. See that? Okay? Pebbled. So what's the significance? A lot of significance, because when this goes this way, it's got a lot of surface area, it can go faster. It can propagate faster. Okay? Right? And then you get strong burning at the locations here and there. So these are real. They're absolutely real. And you have to recognize that they occur in the flame, in your engines. Okay? So let me explain this to you. There are two modes of instability, mainly two modes. One is that diffusion of thermal. If I have a flame which I wrinkle it this way, okay? As I've told you that the thermal diffusion is this way, mass diffusion is this way. So if Lewis number bigger than 1, if I wrinkle it this way, then thermal diffusion is stronger than mass diffusion. It'll make it burn stronger. So it'll come back, spring back. And for this curvature, it's going to go this way, okay? So if I have a planar flame, I wrinkle it. For Lewis number bigger than 1, the wrinkle will come back. The wrinkle will be diminished, okay? So it's self-stabilizing. It doesn't get unstable. On the other hand, if Lewis number is less than 1, if I wrinkle it this way, this burns weaker, but this less than 1, so it'll burn even weaker. Go this way, okay? So Lewis number less than 1 flame is inherently unstable, cellular-wise, okay? Lewis number bigger than 1 flame is stable, give you smooth flames, all right? One thing. So that's one mode of instability. The other mode of instability is hydrodynamic instability. Hydrodynamic instability is it's called Landau instability. Basically, I don't care about diffusion. I just say I have a flame here, very thin flame. I don't care about its structure, very thin here, and it propagates with my laminar flame speed. Now, if I wrinkle it this way, what happens? It's still strictly fluid mechanics, okay? Fluid mechanics. If you see, if I have then the flow upstream of this, the stream tube is going to diverge this way, okay? The stream tube, and it'll go this way. So in this case, you can see if it diverges, then the velocity here will decrease, right? And the velocity here is the same, laminar flame speed. So if I wrinkle it this way, the flame will go this way. I wrinkle it this way, the flame will go this way. Okay? So for this Landau assumption, the flame speed is the same. Flame is infinitely thin. And then if I wrinkle it, the wrinkle will always grow. And that's what Landau proposed in the late 1940s. He said all flames are inherently unstable. It's always unstable. Landau instability. Okay? What I have described for you. Of course, later we find the flames are stable. There are cases, right? But in his limit, the flame is infinitely thin. Remember that. The flame is infinitely thin, then you get that. So flames are inherently subjected to this two modes of instability. All right? This one. So let me show you now the picture I showed you. Hydrogen air, lean hydrogen air. Lean hydrogen air, the Lewis number is less than 1. I just argue for you, okay? Think of it. It's unstable, diffusionally thermal unstable. Then you get this. I guarantee you. You do any experiment, you go back home and do the experiment. That's what you see. It's at 5 atmosphere, equivalence 0.6. It's lean, okay? Rich hydrogen air, Lewis number bigger than 1, it's smooth, it's glass when it propagates. All right? Okay? Hydrogen air, however, for the rich case, it's at 4, it's smooth. But when I go to 20 atmosphere, this 5, this 20, they are all Lewis number bigger than 1. So it's diffusion is thermostable. But when I go to high pressure, it becomes unstable. Okay? So what it's doing here is that when I go to high pressure, this, what's called Darius-Landau, this hydrodynamic instability kicks in. It is diffusionally thermostable, but it's hydrodynamically unstable. Because At high pressure, the flame gets thin. When it's very thin, it goes like a Landau limit. Good old Landau, smart guy, right? Landau limit, it goes unstable. All right? Now, fun part, let's flip, right? So, hydrogen, I do propane, you know the diffusivity switches. So propane, when the Lewis number is bigger than 1, it's bigger than 1. When it's lean, it is stable. Hydrogen, when it's lean, it's unstable. Propane, when it's lean, it's stable. Propane, when it's rich, it's unstable. Whereas when it's hydrogen, it's stable. I'm flipping it, okay? I'm flipping the Lewis number by flipping my mixtures, lean and rich, doing this. And the propane air, 5 atmosphere, lean case is stable. When I go to, lean case is stable, 5 atmosphere. When I go to 20 atmosphere, again unstable. This Landau instability takes you. Okay? So here is something, a thought which is very profound, to me it's very serious. It's not much recognized. I've been advocating it. It's not much recognized, but I want you guys to remember, especially you do engine research, whatever. What I've shown you here is at high pressure, regardless of whatever flame I have, it is subjected to Landau instability. Okay? What does it mean? Your IC engines, your internal combustion engines, your gas turbine, your diesel engine, whatever engine you have, the pressure there is very high. Okay? When you have flames here, there is strong possibility those flames would exhibit Landau instability. They'll be wrinkled. Okay? So what does wrinkle do? Wrinkle can make it burn stronger, but through wrinkles, certain times they can extinguish through this kind of things. Don't know. But you might need to include that. Right now, the wrinkling of flame in all those turbulent flame simulation is really just through turbulence, right? Your turbulence wrinkle the flame and all this. You can do it very well, all this great, or your simulation, great. But hiding in the background, you might not realize is that those flames could be wrinkled. You do experiment, you better check. You better try to find it to see whether they're wrinkled. If they're wrinkled, change your burning rate, they change everything. Everything changes. I don't think it's being seriously looked at. So I don't know who, whatever my comments made would affect whatever you're doing, but you know what I'm trying to tell you. Okay? This is a good research problem. Very good research problem. So, okay. So 4, it's not too bad. But my daily special is on the other side. Sorry, we don't have daily special. So the standard premix flame, the concepts introduced. No, I didn't go through asymptotic analysis. Okay, we talk about cold boundary difficulty. We talk about distinguished limits. Okay, I talk about flame structure based on one-step chemistry and detailed chemistry. Okay, and the further studies, we really need to really understand more about chemical structure of hydrocarbon flames. I have shown you some, just a little bit. It's very rich. You can see that. All right. You want to interpret. Those of you, go home. If you know how to do the laminar flame speed calculation speed, you output the profiles, different reaction rates, and try to understand what they do. Okay. Try to tell a good story. I have shown you I've shown you the hydrogen case. We've done the methane case probably in the book. You're curious? Do it for propane. Do it for the C2s, the ethylene, acetylene, and try to tell a good story like this. The influence of flow structure, the flame structure, on the reactivities. Okay? So low temperature. Now, there's something interesting. Explain the lack of influence of laminar flame speed by low temperature chemistry and molecular size of large N alkenes. Right now, I don't know how some of you know what I'm talking about. There's a lot of discussion in the community about the influence of low temperature chemistry and high temperature chemistry. Anyone know what I'm talking about? You do? Raise your hand. Low temperature chemistry, high temperature chemistry. There's a lot of discussions, okay? There's one school say low temperature chemistry is not important. Don't worry. So too complicated anyway. Let's don't worry about it. There's the other school say no. Low temperature is crucial, and things like that. So I'm neutral. For me, that I say, what's the big deal? I mean, you have to study high temperature. Some people study high temperature chemistry. Some say low temperature chemistry. This, everybody have fun, right? So, why you want to say this, that? So, is it possible to derive a semi-empirical expression for laminar flame speeds based on TA debating? This is my own sort of hang-up. I'm curious about these things. Limit phenomena, extinction is due to insufficient reaction time, while flame blow-out is due to imbalance between flame and flow speeds. So I want you to be very clear about this. The use of the terminology. Don't casually use different terminology. Extinction is not blow-off. Extinction is not blow-out. Okay? Extinction is extinction. Extinction is due to the insufficient reaction time, reactivity in the flame. Whereas blow-out is due to the imbalance in the flow and flame velocity. They're different things, different animals. The disappearance of a flame could be due to extinction, could be due to blow-out. Again, different. When you have the title of your paper, use the right title, Okay? I have seen funny titles. Yes. Okay? Anyway, I'm not trying to, but really know the fundamentals. Extinction is in general caused by enthalpy loss. When I say enthalpy loss, I mean heat or reactant. Reactant gives me the chemical energy. Heat gives me the thermal energy. Any kind of loss, okay, would be, to me, energy loss. In the preheat zone, leading to order epsilon reduction in flame temperature and order 1 reduction in flame speed. So I need to distinguish flame. I didn't talk too much, order ignition flame. What is the fate of a freely propagating flame to increasing strength of the imposed strain rate? So anyway, those things I didn't really go through detail. Need detailed study of the chemical structure of stretch flames, which we haven't done much. So no, I'm not going to go to daily specials. I mean, it's 5:30. You guys want to go to the farewell banquet, right? So, right? Look, give me 1 minute. Let me show you some. Let me show you some beautiful pictures. Okay? Here. Let me show you some beautiful. I want to show you spiral flames. I have shown you cellular flames. Okay, Lewis number less than 1, whatever. Okay? Cellular flame. But when you flip the Lewis number into the other side, on the one hand, it's cellularly stable, but it's pulsatingly unstable. It can go this kind of things. Okay? It can be pulsating. And then it could exhibit what's called spirals. This is a target pattern. When you have a flame there, you see this kind of thing, comes out. And it comes out real fast. The frame rate is 15,000 frames per second. Within each frame, at this one, you got this guys appearing on your flame surface. Okay? I don't know what's the use of this, practical use of this. One thing I can see is that you can train your camera at your flame, and then you can detect this kind of thing, because they usually occur close to extinction. Okay? So they might be the canary bird. the flames about to extinguish suddenly comes. So if you can detect them right away, you do something, prevent and extinguish. There are other things, okay? Just give me another. There are spiral flames. Let me show you. If you look at them, isn't it beautiful? The flame surface, counterflowing spiral flames. They occur. It's no special case. Okay? Spiral flames, beautiful spiral flames. And they can be disordered spirals. If you study a nonlinear mechanics, okay, nonlinear mechanics, that you have a target pattern is a perfect spiral, and then you get spiral, and then you get disordered spiral. And this, if you look carefully in the figure, they got all sorts of things. Okay, disordered spirals, and that's okay. That's good enough. All right. So I see you guys at the reception banquet.